Hi, my name is Stephanie Stacy, and I'm a PhD student in the Stats department at UCLA. My work is on cooperative communication and shared agency. Cooperation can be enhanced with communication, and humans are great at both. We convey rich ideas using sparse and often ambiguous signals. And this is possible because we are able to infer what is relevant using the context of the situation. One powerful type of context within language itself is pragmatics. Here we consider not only the signal that is sent, but also alternatives that are rejected. But context is often completely outside of language itself, and even toddlers are sensitive to this. In the experiment on the right, the same spoken request for help in retrieving a battery has completely different interpretations based on the visual context. When the experimenter's hands are empty, toddlers retrieve the far battery more often, reasoning, if it had been easier for the experimenter to do it for herself, she wouldn't have had to ask for help. And we can attribute this to cooperative logic and joint utility reasoning. So here we propose a computational model that synthesizes different types of contexts for ambiguous communication. And as a model of communication, we need a way to process signals. RSA is a successful model of language pragmatics, where you model your partner directly in a recursive manner for rational communication. However, we're interested in communication that enables us to coordinate together in the physical world, whereas RSA is typically designed for language. And so for this reason, we devised a way to connect signals back to instrumental actions. We can do this through the mind. Theory of mind is a model of social common sense, and it predicts that we act rationally according to our underlying mental states. And by observing others' actions, we can make Bayesian inferences about their hidden mind. However, we're interested in starting from a cooperative standpoint. So the mind we want to model is not individual, but shared. And to understand this, it's helpful to pause for a moment and think about the ideal model of cooperation, a centralized we. This we could seamlessly coordinate us like limbs of a body. But in reality, we doesn't exist. The best we can do is to take all the public information and individually imagine this we mind with joint beliefs, desires, and intentions that produce joint rational actions. And here, communication is what helps us coordinate different versions of the imagined we until they are well aligned for successful cooperation. Once we model the mind, we can make predictions about rational actions. Based on our shared perceptual and physical environment, we connect the utility of a signal back to the utility of an action. And under the imagined we, communication and cooperation interact with each other as mutual constraints. Communication helps align our perspectives to better cooperate, and at the same time, assuming cooperation constrains the interpretation of a signal, allowing us to successfully navigate overloading. So we introduce a task that helps showcase the strengths of social and physical contextual reasoning in the imagined we. And here, a signaler and receiver share an environment with different items, one of which is the target. The goal is for one of the agents to reach the target, but only the signaler knows what the target is. So moving has a cost, and getting to the target produces a joint reward. And first, the signaler decides their action. They can either walk to an item or send an ambiguous signal. And then the receiver has a chance to respond. So we test our model against a set of baselines in two separate experiments. First, we manipulate the amount of overloading by increasing the number of items in the environment. And second, we look at how recursion affects cooperation. So the first model we consider is this optimal central controller, which is the maximum achievable utility in the environment. And all of the other models are measured as a difference from this optimal. Second, we have the do-it-yourself signaler, where the signaler always acts instead of communicating. And then a joint utility only model without pragmatics, as well as an RSA-style pragmatic reasoning model without joint utility. Finally, we have the imagined we. We see that communication improves performance in this task when compared to doing it yourself, except at maximal levels of overloading. And unlike other baselines, the imagined we is able to successfully communicate even under high ambiguity. Finally, since RSA is a recursive reasoning model, we compared performance at different levels of signaler and receiver recursion. In general, deeper reasoning does improve performance. Here, the more blue, the higher the achieved utility. We see imagined we outperforms RSA at all levels, and even a simple model of the imagined we does better than the most complex version of RSA. This means in the imagined we, common sense reasoning and joint utility reduce the necessity for deep recursion. And this just goes to show that conversation should be easy. So in conclusion, we've developed a shared agency imagined we model for communication and demonstrated that it can perform well, even under high ambiguity and without deep recursion. Thank you.
Hello everyone, I am Hiram Nimlekar. I'm a PhD student in the ICRA lab at University of Southern California, and today I'll be presenting our research on two-stage clustering of human preferences for action prediction in assembly tasks. We focus on manual assembly tasks where humans are required for performing the intricate operations like fitting cables or assembling a satellite, and the robot would be in charge of performing the non-value added or secondary work like fetching tools or parts from the storage. So a challenge in assisting workers in these assembly tasks is that each worker can have their own way of doing a task. So they may have their own preferred order of connecting parts or preferred pattern of placing screws. So to effectively assist each worker, the robot must perform the secondary work as per that worker's preference. Therefore, a research question is how can we efficiently learn human preferences in assembly tasks so that new workers don't have to demonstrate their preference from scratch. Prior work that addresses this problem pre-computes dominant preferences by clustering users based on their action sequences. Then, for a new user, we can efficiently infer their preference by matching them to one of the known dominant preferences. Now, we applied this approach for a more complex bookcase assembly task, but we observed that there was a high variability in the user action sequences, making it difficult to cluster the users to a few dominant preferences. But we also observed that users performed the assembly in subtasks of consecutive similar actions. What I mean by that is consider the bookcase shown on the left. So many users performed the subtask of connecting all the boards in a row. And many users also performed the subtask of connecting all the shelves in a row after that. Therefore, we saw that many users followed these similar sequences in terms of these subtasks, but they varied if we looked at their action sequences. So our key insight is that people have preferences at different resolutions, and we want to encode this as prior robot knowledge so that we can accurately infer their preferences. So at a high level, the preference is the sequence of subtasks or events. And at a low level, preference is the sequence of secondary actions within that event. Now, to leverage this high and low level preferences for action prediction, we propose a two-stage clustering and inference approach where in an offline training phase, we collect demonstrations from a bunch of users and cluster them to learn the high and low level dominant preferences. Then in the online execution phase, we observe the actions of a new user and then use Bayesian inference to infer the high and low level preference of the new user. Next, we perform an ICRA assembly user study to validate our two-stage approach. Here, we collect demonstrations from 18 subjects for assembling the bookcase as shown on the right. We told the users to plan for assembling the bookcase as fast as possible, but did not give them any instructions for the order in which to connect the parts. We still saw that most of the users clustered to just 3 dominant high-level preferences. So the first high-level preferences, 7 users performed an event of connecting the boards first, then the event of connecting all the connectors second, and lastly the event of connecting all shelves in a row. Whereas for the third high-level preference, users first performed the events of connectors and shelves to form this lower half of the bookcase, then attached the boards, and then finally connected the shelves to complete the top part of the bookcase. We also saw that in the event of connecting all shelves in a row, users had low-level preferences, where some users connected each shelf to boards on both sides at a time, and other users connected each shelf to one side of boards at a time. Finally, we show how our approach can be applied in a real-world human-robot demo. Here, after observing the initial actions of the user, we can predict that the current event is boards and perform the secondary actions required for that event. In summary, for complex tasks, we saw that users can have preferences at different levels. At a high level, it is the preferred sequence of events. And at a low level, it is a sequence of secondary actions within each event. And we saw how this approach can be useful for action prediction for an ICRA assembly task. In future work, we would explore the usage of this approach for other assembly tasks. Thank you, and I can take any questions that you may have.
Hello everyone. I'm Xiaofeng Gao from UCLA. Today I'd like to talk about our paper, Show Me What You Can Do, Capability Calibration on Reachable Workspace for Human-Robot Collaboration. In human collaborations, it is often beneficial to know each team member's abilities, so that a specific subtask can be assigned to someone who is good at it. We believe that for a human user who is collaborating with robots, understanding the robot's capability would also benefit the collaborations. Take this table clearing task, for example. The human and the robots take turns to clear blocks on the table. The human can reach all 4 blocks, while the robot can only reach the red and green blocks. For such a task, the optimal strategy for the human is to pick up blocks that are not reachable by the robots. If by mistake, the human believes that the robot can reach the yellow block and pick it up, the robot may have nothing to do in later rounds, resulting in a worse collaboration performance. As you can see from this case study, incorrect estimation of the robot's capability may impair collaboration. To deal with issues caused by discrepancies in capability estimation, we envision a calibration phase. That is, before the task, the robot can generate a small number of demonstrations to show its reachable workspace to the human. To make these demonstrations as informative as possible, our intuition is that the robot should take into account human belief of its reachability, so that in the next demonstration, the robot may move its end effector to somewhere in its reachable workspace the human doesn't really know about. To this end, we propose REMP, a reachability expressive motion planning algorithm. This is based on optimizing the trajectory to balance the reachability expressive cost and the physical cost. The reachability expressive cost would encourage an effector to move to regions where the capability is underestimated. The user's belief of a point's reachability is modeled based on its distance to the observed trajectories. If a point is closer to an observed trajectory, it is more likely to be considered as reachable. We first show some qualitative results conducted on 2 link arms and the Peer 2 robots. The trajectories generated by REMP are visualized in blue, and human belief of the reachable workspace is in orange. It is clear that our method accommodates human belief at each time step and tries to traverse uncovered regions to better express the robot's reachability. As a result, the trajectories can cover a large part of the reachable workspace. Now we look at some quantitative results. We simulate the human's estimated reachability after seeing some demonstrations and compare it with the ground truth using an intersection of union measure. Given the reachability estimation, we also simulated the performance of the team in the subsequent table clearing task. Our methods visualizing solid lines outperforms the baselines for all the robots. As we have demonstrated the effectiveness of REMP in simulation, we now turn to investigate how much it will help real humans working with robots. We conducted an online study with 202 participants, manipulated the type of motions participants observe in the demonstrations. In the end, we found that REMP users' reachability estimation of the robots are significantly more accurate. Compared with users in purely functional motions, REMP users are able to get a significantly higher reward in the subsequent collaboration task. They also reported the robots the most reliable, the most predictable, and the easiest to understand. These objective and subjective results together suggest that our approach has an overall advantage for improving humans' understanding of robots, as well as the quality of collaboration over the baselines. In this work, the robot capability we focus on is its reachability. We believe this is necessary since reaching is one of the most basic tasks in human-robot interaction. Nevertheless, REMP can potentially be combined with other approaches to facilitate the understanding of robots' various capabilities. Also, we mainly look at 2D reachable workspace of robots. This is due to the constraints that it is hard to demonstrate 3D positions in the online study. In the future, we plan to conduct in-person study for calibrating 3D reachable workspace. Other possible directions include multimodal demonstrations and online calibration. Thanks for your attention. Feel free to ask any questions.
Hi, I'm Dennis, and I'm going to talk about our method to improve performance on multi-agent coordination tasks by using joint attention. So one of the main challenges in multi-agent RL is that it can be very expensive. A lot of recent approaches like MADDPG and QMix use decentralized execution, where each agent has a separate fixed-sized action space, and this prevents the exponential growth of the action space as additional agents are added. But now, as the agent policies update, the environment appears non-stationary to each individual agent. To address this, it's common to add a centralized critic that looks at all of the actions, but unfortunately, the space of the inputs to the critic also grows exponentially with the number of agents. To address this problem, we drew some inspiration from humans. So when humans coordinate on a task, they don't need to consider all of the possible objects and actions their partners could take, because they have the ability to infer and direct what other humans are paying attention to. This ability is called joint attention, and it's an important milestone in the development of human infants. So we thought this could be a useful inductive bias to add to an RL agent as well. The hypothesis is that agents can learn to filter out most of the environment and only act on the relevant objects. So even though they learn and act independently, because of this bias, they don't need to explore the entire exponential action space independently. So this is an example of the architecture we use for our agents. The important step is highlighted in red. So we generate a bunch of weights over the input image and use a softmax layer to force the agent to attend to only a few objects. This is equivalent to the dot product attention used in transformers, but over the pixels or objects in an image rather than text. We then compare the attention maps using Jensen-Shannon divergence with more similar maps between agents, resulting in more reward. The idea behind adjusting the reward rather than changing the loss function directly is that the agents can then trade off a more accurate match now in order to learn to help the team improve coordination later. So for example, it can move its focus onto a different area and take a step in that direction in order to draw the attention of the teammates to that area. For the environments, we use a couple of grid worlds with coordination tasks, such as meeting up at the same location, gathering items of the same color, or collectively hunting a high reward stag rather than independently gathering low reward berries. Our experimental results show that restricting the agent's attention to a few objects improves performance, and encouraging those attention maps to match improves the results even further. So here we can see the attention maps on the stag hunt task, where the movement of the agents is on the left, the attention of the red and blue agents are on the middle and right. The larger circles show more recent attention, while darker circles show stronger attention. And you can see that in the joint attention agent on top, both agents focus on the stag in the bottom right corner, while in the baseline agents below, the agents move to collect their own berries and do not coordinate. Another interesting result is that matching attention with an expert can improve learning. So we have a complex multi-step task that each agent must complete independently. But in this situation, focusing on what the expert focuses on can improve learning speed, since it again filters out the irrelevant parts of the environment. So yeah, we provide a new attention architecture and attention matching incentive. In humans, joint attention helps with coordination and learning from experts, and we show that in our method, it helps agents with providing the same benefits. We're still missing the other part of joint attention, which is the ability to direct attention explicitly. And we think that this method in general could be interesting to apply to human AI interaction as well. So thank you for listening.
Hello everyone, I'm Minglu Zhao from Dr. Tao Gao's lab at UCLA. Today I'll be presenting our work titled Sharing is Not Needed, Modeling Animal Coordinated Hunting with Reinforcement Learning. Reinforcement learning is a state-of-the-art artificial intelligence algorithm with agents learning from trial and error. Multi-agent reinforcement learning settings extends the single-agent settings by assigning the same reward function to agents, effectively letting the agents share the group reward. And under this approach, the algorithm has achieved successful coordination in many different domains. However, from a cognitive perspective, cooperation is more complicated than simply sharing rewards. Many factors, including punishment, commitment, fairness, and ownership, are considered as necessary to support human cooperation. With this contrast of human social intelligence and reinforcement learning approach, we're curious that without these complicated concepts, and simply through sharing rewards, is the coordination model through multi-agent reinforcement learning robust? Furthermore, we're interested in the idea of sharing rewards from an animal cognition perspective. So some studies claim that chimpanzees play complementary roles during coordination, which shows that they're truly cooperative. However, other studies argue that chimpanzees can still display this behavior even if they work only for selfish interests. So with this debate, we're interested in whether sharing rewards is necessary for coordination. So to test these hypotheses, to test these questions, we use a coordinated hunting task as illustrated over here. In the environment, we have multiple predators chasing for one prey, and the predators have individual action costs, and they are rewarded only after kills, which happen in 20% of all biting instances. In our experiments, we evaluate factors that have evolutionary importance. The first one is the reward distribution after kill. Here, we introduce the concept of the predator's selfish index, which manipulates the reward distribution as a function of the distance to kill. And purely selfish agents over here have an infinite selfish index and will only reward itself when it kills the prey. And purely unselfish agents have a selfish index of 0 and will evenly split the reward. The next factor we're interested in is the free rider problem. The free rider problem is a critical challenge for coordination. It refers to the scenario when some agents in a group receive the reward even though they did not put any efforts into achieving the success. In our experiments, we manipulate the severity of the free rider problem through different levels of action costs, which is defined to be proportional to the force exerted. Next, we're interested in the effects of hunting party size on coordination. So here we have different numbers of predators. Lastly, we manipulate the difficulty of hunting by varying the speed of the prey relative to the predators. For modeling agents' behavior, we adapt the algorithm of multi-agent deep deterministic policy gradient, and this is an illustration of the algorithm. Next, I will show some demos for our trained models. First, we look at the results when having a small group with 3 predators and no action costs. So to the left, this is for agents with individual rewards, and to the right, this is for agents that share rewards. In this case, agents under both settings can successfully coordinate. Next, we look at the results when having a large group with 6 predators and no action costs. We can see agents with individual rewards can still coordinate. However, agents that share rewards fail to coordinate and even have a worse performance than when the group size is small. Next, we look at the demos for a medium-sized group with 0.1 action cost. We can see that the coordination for agents with individual rewards is still successful. However, when agents share rewards, there's almost no movement for the entire group, indicating a free rider problem. And here are the results of our experiment. So back to our motivation questions. We conclude that first, coordination through sharing rewards is not robust. And second, sharing rewards is not necessary for coordination. So that's all for my presentation, and thanks for listening.
Hey everyone, my name is Zhishuan or Just Shuan. I'm a PhD student at MIT and use they, them, or she, her pronouns. I'm excited to share its brief overview of her paper, Modeling the Mistakes of Boundary Rational Agents within a Bayesian Theory of Mind. This is joint work with Arwell and Curry, Gloria Lin, Joila, Vikash Mansinka, and Josh Tenenbaum. People routinely infer the goals of others by observing their actions over time. As this well-known video shows, we can do this from a very young age, as young as 18 months old. As you're watching this video, notice what happens. The adult pursues a very strange and suboptimal plan. Indeed, you could say that the plan just fails. And yet, the child is able to infer what the adult probably wanted, and it's the recognition of this failure that leads the child to offer assistance. The question then is, what explains this rich and flexible capacity for mental inference? How are we capable of inferring the goals of others even when they fail to achieve those goals? Our hypothesis is that humans intuitively understand that others might make mistakes and account for them when inferring goals. A classic example is inferring that others might have mistaken beliefs due to observing incomplete data. We're interested, however, in mistakes that arise because we are, at best, boundedly rational. This includes failing to execute actions as intended, misguided plans that fail to achieve our goals, and even confusion or conceptual errors at the level of goal formation itself. We can formalize this hypothesis by specifying a Bayesian model of a boundedly rational agent as a probabilistic program. The agent has an initial goal, but at every time step, it has some probability of confusing that goal with a semantically similar state, or perhaps recovering its original goal. This accounts for potentially mistaken goals. The agent then plans to achieve that goal, but in a boundedly rational manner. In particular, the agent doesn't form a complete plan from the start, but instead plans only some steps ahead, executes those steps, then replans as necessary. Replanning in this way is less cognitively demanding, but can also lead to suboptimal or mistaken plans. Finally, the agent executes its plan. However, due to execution error or motor noise, the agent may sometimes execute a random action instead, that is, a mistaken action. This animation of a gradable agent illustrates the most complex part of this process, which is the partial planning. Red dots represent states explored during an A-star planning algorithm, and blue dots represent partial plans that the agent executes. So that's the agent model, and we hypothesize that human observers perform Bayesian inference over this model. We implemented this tractably using a particle filtering algorithm, sequential inverse plan search, the details of which can be found in our earlier NERDS paper. To validate our model, we conducted experiments where we elicited goal inferences from human observers as they watched an agent interact with an environment, sometimes optimally and sometimes suboptimally. These trajectories were designed within two domains, a grid world puzzle with doors, keys, and gems, and a blocks world environment where an agent spells words out of lettered blocks. Now I'll show a couple of illustrative results. Watch this agent and try to guess which color gem it's trying to pick up. Notice that the agent exhibits a suboptimal plan, backtracking to pick up a key in order to reach the red gem. Our model accounts for such planning mistakes because we assume that agents can always plan fully ahead. Its inferences closely match average human judgments, in contrast to the Boltzmann agent model, which only accounts for action mistakes. Now let's consider a different kind of mistake. Take a second to figure out what the agent would have to do to reach each gem in this environment. Got it? Now watch what happens. So most people watching this would say that the agent was trying to reach the red gem, but got stuck because it didn't realize it needed two keys, not just one. Again, our model accounts for this inference because it allows for the possibility of myopic plans, unlike the Boltzmann agent model, which attributes all missteps to just action noise. Finally, let's see an example of mistaken goals. Watch as this agent stacks lettered blocks and try to guess what word it's trying to spell. Did you already manage to guess cower? If so, you're like our other human subjects, who accounted for the possibility that words might be misspelled. An instance of goal confusion in this context. Our model was able to do the same, assigning cower as the most likely goal once its misspelling was observed. Overall, average human judgments correlated highly with our model, and more strongly compared to the Bayesian or baseline models. We think these findings provide considerable support for our hypothesis, indicating that it is important to model errors at multiple levels of cognition and action to build an intuitive theory of our boundedly rational minds. That's all the time we have, so I'd like to thank my co-authors again, and I hope to see you all at the poster session later today.